Okay, so the goal of this video is to um, look at graphing cardioids and then also look at graphing what happens if your cardioid sort of changes slightly and becomes like a limacon. And limicones either have roots or don't have roots. So what I have right now are four equations of cardioids. And what makes a cardioid is that the coefficient that we would normally think of as like a vertical translation and the amplitude are identical. And so, like, if I think about this just in the normal xy plane, like, what if it was like y equaled 4 plus 4 cosine of x? So I know my amplitude is 4, and I know my vertical translation is also 4. So just looking at that one period, like I could think about the new line of symmetry would be 4 units up. And then when you draw your cosine graph, you would start 4 up and come down and would touch right on the x-axis and come back up. In other words, because these two values matched, the low point is going to be right at 0. And in fact, all four of these functions, if you were to think of them in their xy or rectangular form, like this one right here, like y equals 3 plus 3 sine of x, again, just looking at one period, the fact that my vertical translation is up 3, but then for my sine function, I start at the level of equilibrium, I go up, I come back down, and I go back up. Again, that one moment in time when you're at your lowest, we are crossing the x-axis. Or sorry, we are touching the x-axis. We're not crossing it. So what does that mean when we think about graphing a polar function? Well, we already had learned for polar roses that every time a sine function in general or a cosine function in general, right, it just keeps going on forever and ever. Every time it crosses the x-axis, that's when our polar function went through the pole. So now we're going to just be touching the x-axis and then not going through the pole, just bouncing right back. So if I think about what that might look like, let's use Desmos to help us out. Okay, so Desmos, the one I want to look at is here. So if you take a look, I've got 4 plus 4 cosine theta. So let's see what happens when I graph this. So notice that it's starting out at the highest point cosine is, and it's coming in, and it's going to get really, really close to the pole, or 0, right? So at that moment in time, I have a radius of 0. But instead of crossing through, what ends up happening is it bounces back out. And so we create this cusp. And that cusp is exactly where the other graph would have just touched the x-axis. Now, I can certainly change that from a dotted line to a solid line to maybe see that a little bit better. But again, here we are. We're going into that cusp. And then it comes right back out. Okay, so the fact also that when we graph these functions, notice that it's just a theta. It's not 2 theta, 3 theta, 4 theta, 5 theta. We're not changing frequency. We're simply changing the translation, what used to be a vertical translation, and then also our amplitude. Now it just hits that perfectly, right, in a perfect cusp, and then bounces its way out. Now, the other thing I want us to notice is that when I have a cosine function, which is positive x, or we think about cosine as the x direction, my graph has a line of symmetry along the positive x. If I were to change this and write as, I don't know if I can do this. Sorry, I apologize. I don't know if I've done this with a stylus. Let's see if I can do this. Nope. Oh, here it is. And I want to type in sine. Sorry for the delay. If I go sine, and now I take a look at this, notice that I'm still going to have a cardioid, but watch what happens. Because sine is associated with the y value, my function's going to be along the y-axis, but it's still going to be a cusp because the two values, those fours, they are exactly equal. So it's going to go right to that cusp and then push out. And I would just be keeping track of quadrantal values. And, if I had a negative cosine, it'd be on the negative x, and if I had a negative sine, it'd be on the negative y. Now, what happens if instead of having them equal to each other, what if my function were, let's say y equals 5 plus 4 cosine of x? In other words, my line of symmetry is greater than the amplitude. So if you think about what that might look like, so you have your line of symmetry at 5, but your cosine is only having an amplitude of 4, which means it's never going to quite touch the base. So if there's an absence of great crossing the x-axis right there, that means in its polar version, it's never going to hit the pole. So when this number is larger than our amplitude, we no longer get a cardioid. It starts to try to create a cardioid, but what you're going to end up seeing is that as you approach the pole, instead of going in, it gets pushed out. And again, it does not go through the pole. So let's take a look at what happens there. So I'm going to change this first coefficient to be bigger. Let's say 5. So now we can see, right? So now we can see it never really got into a cusp. So we start our normal, we're starting at 0, you're finding a radius, but then watch what happens as we begin to try to approach the pole. It doesn't intersect, it pushes out. So this is called a limacon, and a limacon could have a loop or not have a loop, and this particular one does not have a loop. Now, if I think about what if that was reversed, in other words, what if my vertical translation wasn't as big as the amplitudes? What if I said this is 3 plus 5 sine of x? And again, I know I'm using the rectangular form to help me graph the polar, but a coefficient of 3, so it means my vertical translation is up 3. So this distance is only 3. But then when I graph sine with an amplitude of 5, I'm starting here. I'm going up 5, and when I go down 5 and go back up, I clearly cross the x-axis and I go negative. So I have to somehow go cross the pole and go negative for my radius. And so that will always happen if this lead coefficient here is less than the amplitude. And so I know I've already talked about these being limacons. It's very fancy, right? It's French. So this is a limacon. And there's a soft C, that's why there's a cedilla under the C. So a limacon is when your coefficients don't match, whether it's a one, like the first one's smaller or the second one is smaller. Those are limacons. This one will have a loop, and we'll see what that looks like. Where this one up here we just did was a limacon without a loop. Okay, so let's take a look. First thing, let's go ahead and just do cosine, just look at something different. So let's look at cosine. So it should be on the positive x, no surprises there. So there's cosine. No loop. And remember, if these are equal, so if that's both a 4, that's a cardioid, and we get the cusp. But watch what happens. Let's pause for a moment. Watch what happens when that first coefficient is less. Let's say 2. So we'll hit play. It again starts as if it's doing a cardioid, but eventually we get to the pole, and notice it's continuing in itself with a negative radius. It's going to go right there. Oops, sorry. A little bit. I was trying to get exactly pi, so pretty close. So right at pi, we're halfway through. And even though 180 degrees is pointing towards the left, we have a negative radius, so it's behind it. And then it continues on through. So it's like a cardioid where the cusp collapsed in on itself. and we get something that's sort of like an inner loop. Now, the length of the inner loop is 2 units. Not a coincidence because that's what the difference of 2 and 4 are in the coefficients. And so we get this, this limacon without a loop. Now, if you made that a -4, we should be on the negative x-axis. So again, it just kind of flips to that side right there. So cardioids and limacons are kind of related. Remember, cardioids are when they are exactly the same. So if I would have changed that 2 to a 4, so they're equal to each other, then it matches a perfect cusp. And if you think about your trig function, sine or cosine, that determines if it's the x-axis or the y-axis. And if it's a negative cosine or positive cosine, then is it on the left, right, or is it up or down? Okay, so again, here's a cardioid. Now, if I want to look at a limacon without a loop, remember, I would just make, we'll go positive here, I would just make this first number larger. So let's say I make that a 2 cosine. So what's happening is that I can never get into the cusp. And in fact, because the difference of those two values is 2, that's how far away I'll always be from the origin or the pole. Now it kind of looks like a circle that got punched in and flattened, and that's because that's the cusp trying to meet. Okay, so how are we supposed to then graph these and think about these without a calculator, right? So cardioids, like we said, here's the definition of a cardioid. So a cardioid only is going to be a sine or cosine, and notice the matching coefficients. Cardioids, these coefficients will always be the same. In other words, the translation that we used to think up down and the amplitude will match. And the other thing I want to point out is that we are just a frequency of 1. So that means we don't have to do like 90 divided by 2, 3, 4. It's just 90, 180, 270, and 360. Okay, so let's graph one of these cardioids by hand. We'll pick this one right here. And so since I'm just worrying about the quadrantal values, I'm going to make a little table off to the side. I'm going to, do my r's, do my thetas. And it's just the quadrantal, so 0, 90, 180, 270, back to 360. So we just put in 0, so cosine of 0 is 1. 3 times 1 is 3, plus 3 gives me radius of 6. And then cosine of 90 is 0, so then I just have the initial coefficient of 3. 180's cosine is -1, so 3 minus 3 is 0, so that's where my cusp is going to be. Should be, kind of thinking and anticipating that. 270, the cosine is 0, so we're back to 3. And 360 is the same thing as 0, so we're back to 6. So this function is going to start at 6, 0. 1, 2, 3, 4, 5, 6. We can put a little star. So it's starting at 6, 0. And then it's going to go in a counterclockwise direction to 3, 90. And then it's going to get to the origin at 0, 180 degrees. And then it's going to be at 3, 270. And then back to 6, 0. So what that looks like, again, moving in a counterclockwise direction, thinking about a cusp. So we come up, kind of fan out. We start to head into the origin. Right there is my cusp. And I try to make it symmetrical coming around. And we always move in that counterclockwise direction. And so just throwing on some arrows indicating that's the direction that we go. Okay, so that's a cardioid. And again, what I wanted us to notice is that 3 plus 3 is 6, and it's on cosine. So I'm thinking that this here is 6 units long, right? It's on the cosine. And then this is 3 units this way, and that's 3 units that way. Okay, the same concept is going to happen when we look at a limacon. And there's my soft C. So notice how close the limacon is to a cardioid, right? The coefficients are different as opposed to being both the same. So it's kind of like a mutation of a cardioid. Now, if your first coefficient is smaller, and we saw this already, so as an example of a smaller one, like r equals 2 plus 5 sine of theta. Since my vertical translation is not as great as the amplitude, that means when I graphed, if I would have graphed it on the normal xy coordinate system, I'm going to actually dip below and therefore get um, an inner loop. So if the first number is smaller than the second number, then the limacon has a loop. But if it's the other way, if the first number is bigger, you're never going to cross the origin, so then there is no loop. So the limacon has no loop. Okay, but again, look at your frequency, just theta. So we only have to check the quadrantal values. So let's do one of these together. Let's do A, 2 plus 6 cosine of theta. So I already know that these numbers are different, so it's no longer a cardioid. I also recognize cosine, so it should be on the positive x. So let's do our quadrantal values. So off to the margin here, I'm going to do r's and thetas. If you've noticed, if you're like me, that's backwards. It's so much easier to go theta than r, but you know, it is what it is. So 0, 90, 180, 270, back to 360. So again, thinking about cosine of 0 is 1. 1 times 6 is 6, and 6 plus 2 is 8. 90 degrees is nothing for cosine, so we just had the initial 2. 180 is negative 1, so we've got 2 minus 6, so negative 4. 270 gives us another value of 2, since cosine of 270 is nothing. And back to 360, which is the same thing as 0. So when I graph this, I'm starting at 8, 0. And if I remember correctly, I think I forget to give that to you. So there's 8. So put a star, 8, 0. Now, the next thing I'm getting is 2, 90. Just right there. 2, 90. And then next I need to get negative 4, 180. Well, remember, 180 is way over here, but negative radius puts it back here. So 1, 2, 3, 4 right there. So there's negative 4, 180 degrees. And then we're back to 2, 270, which is right there. And we get to 360, which is our first starting point. Remember, we go counterclockwise. And then we have to, kind of hit our key points. I'm going to start here. And I need to get to there next. So kind of go in that counterclockwise circular motion. Coming around. Now I do have to get through the pole and continue that curvature to, oops, sorry about that. Continue that curvature to make the loop. I accidentally hit the new screen when I turned my computer. So I need to get into that loop. So again, I'm going in this counterclockwise direction. And then, oops, sorry, I'll continue to go out in this direction. I don't know why it's not writing. I think I have my color picked. There it is. Okay. Yeah, so we'll just continue to go all the way through and continue to go out through the loop. So again, we're focusing on a counterclockwise direction. So I'm going to go ahead and put those arrows in that direction. And the smoother you can make it, obviously, the better. But if it's your first time, right? I mean, it's going to take some time. But again, just thinking about going, and I'll maybe highlight it in green. Again, we're starting out here and we go out, smooth direction, curvature in. We go back out, smooth curvature, and we go back out in that direction. Okay, so I want us to know that really limacons and cardioids are very much related, but it just depends on if the coefficients are identical or if they are great, one's greater than the other. So as we start graphing these, it's okay to look at Desmos, but our goal is to be able to graph these without the aid of a calculator graphing device.